Hey guys, welcome back to another episode of the Real Hacker Hours podcast. Today we'll be going through Module 7 of Nightmare. We'll be briefly reviewing the 3 write-ups, making sure that they make logical sense, and porting any Python portions such as the exploit over from Python 2 to Python 3 since Python 3 got end-of-lifed a while ago. Excuse me about that. Had a little burp. Okay, cool. Let's get started, and I think we're going to start with Speedrun. Since these are statically compiled, meaning that libc was actually merged into the binary, it's not linked when it first runs. These binaries are massive, so I already imported them into Ghidra and analyzed them to hopefully prevent that. But let's first take a look at the write-up. I'm going to pull that up. Okay. And I'm also going to navigate to it in this terminal. Actually, no, this is the Speedrun. Okay, 64-bit. Let's run checks like on it, make sure that matches. Partial run, no canary, NX enabled, no pi. Okay, that checks out. Okay, cool. But all of this checks out, so let's start reading it. So we can see we're dealing with a 64 statically compiled binary. This binary has non-exec NX non-executable stack enabled, which means that stack memory is not executable for wireframe. On this, you can check the memory mappings with the vm map command while the binary is running. I think I had that part in there since is the last part. Yeah, last part is called show code off the stack, so I just wanted to show that. Yeah, this portion checks out. Here we can see the memory region for the stack begins at. I think this is just an explanation for like, hey, the stack is non-executable. We can see that because the memory region here is not marked with an X, just RW. Also, since the binary is compiled, that means the libc portion of the binary needs. So libc is not. The binary essentially just prompts us for input. When we take a look at the binary gauge, we see a long list of functions. Code. We can use backtrace. Okay, so in here we find the main function via backtrace command. I wonder, can we just search for main? Nope. Okay. Okay, that's the entry function. We could also go to the entry function. This is not it. Pretty sure this is main. If you go to entry, yep. Entry, this is the libc start do main, whatever the basic function that sets up the binary, and the first argument to it is main. So also the reason why entry typically that needs to be named is since that's the first function that is actually ran to help set up the binaries, and when the environment is actually running the binary, it needs to know that function, so it typically has that symbol. And here we can see that this calls several different functions. However, I think this is the function that actually does. Okay. Also, another thing, typically when a binary is dynamically linked, meaning libc is linked at runtime, decompilers like Ghidra or analysis tools like that will have a much easier time detecting like, hey, this is fgets, hey, this is printf. Reason for that being is it actually needs to define symbols. That way, when it is actually going through the linking process, it'll be like, hey, this is printf. Okay, this function gets yeah, this is printf. That way, when it links to libc, it can successfully link that way. Since this is statically compiled, all of those functions like printf puts are all part of the binary, and as such, it doesn't need to actually identify during runtime, so it can strip all of those away. So this is probably puts, judging from the fact that it's printing out a char pointer any last words. This is probably freed. Let's see. If it gets char pointer, no. Okay, I forget what off the top of my head. It's one of the functions that scans in data from a file descriptor 00, I believe is standard in. I'm just gonna Google this real quick. Standard in 0. Yeah, standard input is 0. Okay, so it's scanning in from the file descriptor 0, which is standard input, into this buffer array, which is OX408. So 1032 and 2000 bytes. So we obviously have a stack overflow. And it gives us a stack leak, which I don't think we'll need. No, it's not a stack leak. It just prints our input with %s. Because the last section had a lot of stack info leaks with printf %p, my brain just automatically assumed incorrectly that it was, but no. So, okay, cool. Let me just go through and make sure this write-up says that. Functions. Okay, we find that. Just gonna add a little portion here about entry by looking at the entry function. So you can see it prints out a message. I'm gonna copy this. Okay, added a little part in there about finding it via just looking at entry. Okay, I'm just gonna read through it to make sure everything makes sense. Okay, it looks like here, if we backtrace to main, this function at A0, where is it? Wait, A to A0, it's not called in here? That's, okay, this is really weird. Why do I have this portion here? Where is this referenced? Oh, okay, so this is the function that's actually responsible for scanning it in. Oh, okay. Yeah. Okay, so that's just me looking at the function for scanning it in. Okay. Yeah, this portion is just me actually looking at that function like fread or whatever it is to actually see like what is this under the hood. When I was just doing here, I kind of just like looked at the arguments and looked at where it was and just kind of put two together. Yeah, two and two together and just assumed what it was. Okay, this portion here I'm actually talking about. Okay, so we have established with all of this stuff, and then above this point on the right that we can do a buffer overflow. Here we're talking about how we are actually going to be landing this via making a wrap chain from the statically compiled binaries, or from the statically compiled binary, which is the target. Be making a wrap chain. This is just me explaining what the wrap chain is going to do. Okay. Let's see, the difference is 0x408 bytes. That corresponds with what Ghidra is telling me, so that's accurate. So far, I've been fortunate with all of the offsets that Ghidra has at least given me when I'm looking. Does correspond to what it actually is. The offset between the start of that input for the char array and the return address, however, that isn't always accurate from what I've seen. Okay, next we're going to be using this rough gadget finder. Okay, this portion I will need to be replacing with Python 2 code. Oh, Python 3 code. Okay, cool. So this write-up looks primarily correct and good. I'm just going to go ahead and port the Python 2 ports over to Python 3. Python 2 ports being the exploit and the running ROP gadget. So let's go ahead and do that. First, let's take a look at the exploit. Let's port this over to Python 3. What will need to be changed? This looks good. This looks like it needs to be changed. Okay, that looks good. And that should be it. Let's try it. Okay, yep, that works. Let's go ahead and copy this over. Okay. So we ported over the exploit portion now for the ROP gadget. Don't think I have ROP gadget on here since this is a new instance, so I'm going to need to set it up. Let's go ahead and clone this, and I get the feeling I'm going to need to install Capstone as well. So yeah, let's go ahead and install Capstone because I'm pretty sure I need that to run this. Actually, let's just see if it'll run without it. Pretty sure it won't. No, look it like it is. I'm just going to go ahead and copy. Actually, let's copy ROP gadget over to the directory. Bit of a janky way to do it, but oh well. Gotta just copy this command basically. Okay, for some reason this isn't finding quite as many. Oh wait, that's because okay, I'm running a bunch of different commands here. Okay. Let's copy this over. Let's copy this over. Let's copy this over. Oh wait, I failed copying that. Why can I not copy? Oh wait, yeah, I'm really smooth braining this. Okay, so let's copy. Okay, cool. So let's just make sure that we have our route gadgets that we need. 415664, 415664, yep. 400686, yep. 410153, yep. And 4498B5, yep. Right there. And we need this one right here. Let's go ahead and run it. And let's make sure 40129C, 40129. Why is this not finding it? Rip 40129C. Okay, I think I know. I think this grep is slightly wrong. It's obviously finding the gadget here. However, when oh, I think I know why. I'm pretty sure I messed up the grep. Okay, yeah. I'm just making smooth brain mistake after smooth brain mistake here. Let's replace this. And let's do this one. For AD251. Yep. Okay, we found this one. And cool, we ported this. Okay, so just to review, I'm just going to briefly read through this portion. First half of the write-up was basically explaining, hey, this binary has a buffer overflow that we found doing this. And second part is, hey, we're going to use a statically compiled rob chain. This is because that the binary is statically compiled, so it has a ton of gadgets for us to choose from, and there's no pies to know the address of all of them. And this is how we are going to, excuse me, this is how we're going to build the route chain and do it. And yeah, so we need 4 gadgets for the addresses. Okay, this looks good. Okay, cool. So this one is ported. I'm going to go ahead and pause before moving on to the next one. Okay, I'm back. Let's do the other DEF CON Quals 1 2016 FeedMe. So I'm going to go ahead and open up the write-up for that. Okay, cool. Let's take a look at the binary. Quals 16 FeedMe. Okay, I think I remember this challenge. Okay, cool. So we see that no row, no canary found, NX enabled, no pi, that matches this, 32-bit binary, 32-bit binary, and the outputs match. When we run the binary, you see that it kind of prompts us for multiple inputs. Let's redo this. So dealing with a 30-bit with a stack when you run the program, prompts us with FeedMe input, and we also see that. Okay, so basically what I said. Okay, I think this is the first challenge that we do that has a stack canary. Stack canary is a mechanism designed to prevent buffer overflows, effectively puts a piece of data between all the variables on the stack and the return address, and before it returns, it just checks to see if it's been overwritten. Since if you to do a buffer overflow to overwrite the return address, you would have to overwrite the value of the canary. No, it doesn't have a stack canary because Punches looks for libc call that due to how it's compiled isn't. Just realized that's misspelled. So effectively what this is saying is, so this program, it'll take in multiple inputs. Obviously we have a stack buffer overflow, but it has a canary. Checksec does not detect it. It has a canary, reason for it being apparently how pwn checksec will check for canary is if a certain libc function is called, which pwn checksec isn't seeing that, partly because it's statically compiled, and I'm assuming the symbols are stripped, symbols being like the names of functions. Looking for references to the string feedme, we find this. Okay, I'm going to go ahead and open it up in Gauger now. Okay, and here we find it via looking for strings, but I'm lazy, so I'm just going to go to the entry function. Okay, here we go. Feed me, I'm guessing. Okay, this isn't working. I'm going to go to the strings. Show references to address. Okay, this is looking like it. Feed me. Yeah, this is looking like the same function here. It's going to start off by we can see it starts by establishing the stack canary. Stack canary is right there, and we see the check happen right here for the canary. We can also see local 10, which is the canary, if you look at the stack layout, we see it's the last piece of data on the stack, or actually, first, yeah, I guess it would be the first one. Yeah, it's the first one on the stack, meaning that it's closest to return address. So if we were to do a buffer overflow, we would have to overwrite that. 60 starts by establishing stack canary, pressing that we'll call a function called puts. I say it's called puts because okay, basically it acts like puts. For seeing that, it will call get int, get some integer, the arguments of okay, here I actually went through the effort of reversing a scan in memory. 8. First you see GDB to follow a fork. Okay. So effectively, from what I remember from this challenge, what it does is it will spawn a child process. That child process is where we actually give an input. We give some input to execute a buffer overflow attack. We will crash the child process and just spawn another one and we're right back at it again. That's why, as you see here, we can smash the stack multiple times and the program is still going. If I recall correctly, how we solve this challenge is a 32-bit binary. The canary is only 3 bytes, so we effectively just brute force it 1 byte at a time. And that's how we solve it. I'm just going to go through this write up and make sure that's what it says. String return to us, which corresponds to the ASCII 7. You see this scan memory function took 2 arguments. Output scanned the size of bytes. Pointer. Okay, it looks like FeedMe. Okay, so it looks like it's prompting us for 2 inputs. First is prompts us for an integer value, and that integer value, I think from what I'm seeing, looks like it's a size that we are actually scanning in. See the last function return a point to this bytes input, which see the offset from the input is stack canary and the return address. Okay, here we're calculating the offset from the start over input to the stack canary. Okay, I'm just going to go ahead and port this Python 2 portion over to Python 3. Literally should be exactly the same thing, but I like just to double check to make sure I'm not smooth braining it. Okay. You see the offset. Stack canary is OX20 bytes and the offset to the return address is OX30 bytes. Does that make sense? I believe this is where input is. 30, yeah, OX30, yeah, that's making sense. The stack canary is at OX10, our output's at OX30, so OX20 offset to the stack canary and OX30 offset to the return address. Both relevant in the reach of our buffer overflow, that is true. Let's see what the FeedMe function is called. You see that backtrace using GDB. Going through the backtrace leads us to the following function. So you see our calling child process and a loop that will run for 800 times. Okay, that means I can crash child process a lot of times around 800 before the program exits on this. Okay, this exploitation basically explains that, like, hey, we're gonna bypass the canary via just brute forcing it since it's only a 3-byte overflow. It should only be 255 times to overflow each byte 3 times. What is 3 times OXFF? 765 times, which is below 800, so we should be able to overflow and get the canary, and then actually overflow and get code execution. And for that, we're just going to be making a route chain fairly similar to the one that we made in the previous challenge. We just read through to make sure it makes sense. Something else is a stack canary, however, we can brute force this process. You have 4 bytes, 1 no byte, and 3 random bytes, so we only 3 bytes you don't know. By the way, for a 64-bit, I believe it's 7 random bytes, 1 null byte. Do this if you overwrite the stack canary 1 byte at a time. The byte we overwrite it with will essentially be a guess. If the child process dies, we know that is incorrect, and if it doesn't, then we know that our guess was correct. There are 256 different values that 1 byte can be. Since there are 3 bytes, we're guessing that gives us 256 times 768 possible guesses. I believe that math is wrong. I think it's that it's 3 times OX 255, since 256 is 1, so it's OX FF times 3. I'm just going to go ahead and change that. If we guess possible combination to guess every combination, if we guess 1 byte at a time, which can't be done by only overwriting 1 byte at a time. Byte canary. With that, we can deal with the stack canary. Also, another thing, I don't think I mentioned it here. I'm gonna need an output or input. With this model, each of the subprocesses will have the same stack canary. That's why we're able to brute force this. This is possible since all of the child processes will have the same stack canary. I'm just going to read through this one more time to make sure this makes sense. Oh, I already have that right there. Okay, added a part I didn't need. After that, we will have the stack canary, and nothing will be able to stop us from getting code execution. Then the question comes up what to execute, and X is turned on, so we can't jump to the shellcode. Place tag, however, can't use route chain. First, we look for route gadgets using we look for the gadgets, and then we build the route chain, and then I exploit and rerun it. Since this is running over 30 minutes, I'm just going to go ahead and just port the exploit portion over and then end the episode. Let's do this. KnownCanary. Where is KnownCanary used? KnownCanary. Okay, it's actually being sent. This needs to be a byte array. Hex canary, representation of the hex. I think that can stay that way. Lockdown.info. This needs to be a byte array. I get the feeling this is going to be very fun to port over. Just probably going to miss a few things. Can replace. Need to switch these over to bytestring. The length of the payload. Okay, let's try running this. Probably not going to work because I missed something. But we'll be able to see what I missed. Xrange 19. Yeah, xrange doesn't exist in Python 3. It's just range. Line 23. What's happening in 23? Input bytes P32. Okay, it appears that it is interpreting this byte string as an integer. Let's see. Print length pack 32 imp bytes 4. Okay. Yeah, we can't just. Oh wait, let's get rid of this length. Is the issue this? Oh, okay, so what's happening is in the current input size. So one thing with Python 3 is with the byte string, if you're iterating through individual bytes, sometimes it will get interpreted as an integer. Like for instance, Python 3 x equals b 0, 1, 2, 3 for I in x, wait, hang on, I did that wrong, for I in x, I. Notice how it prints out 48, 49, 50, and 51. That's because, as you can see here, 0, 1, 2, 3. So what we need to do is we need to specify this is going to be back as a, what do you call it, bytes, ut coding equals, I think this is the syntax, I'm probably going to Google it. Okay, I'm just going to take a second and Google like what the syntax is to convert integer to byte string. So the syntax is just the integer dot 2 bytes parentheses followed by first argument being the number of bytes you want to convert and the second being the byte order, either big endian or little endian. So I should be able to port this by doing 2 bytes, 1 byte order equals little. Let's try this. Can't connect. Yeah, I can't concatenate int 2 bytes. Yeah, one thing that's a little annoying about dealing with Python 3, the exploit dev, is the like byte string conversion shenanigans you have to deal with, which you didn't have to in Python 2. A bytes. Oh, target.receive until this needs to be byte array. That needs to be byte array. Okay, let's try this. Okay, it looks like it's going through. I should probably delete this. Okay, we see the script. It will print out the canary one by one. Looks like there's an issue here. 34 bytes equals can concatenate int to bytes. Known canary. I wonder, can I? Known canary. Known canary is. Oh, I have to convert this over to bytes, I'm pretty sure. So let's go ahead and do that. Okay, let's see. Does this work? Okay, we're halfway through the possible bytes for the first one. Should be coming up soon. First argument must be string, no bytes, new canary. Oh, okay. New canary, it's a string, not a byte. String. Okay, let's see. Will this work? Okay, yeah. the process of a concatenating a byte is figured out the first byte onto the second byte now. Looks like it's figured out the second byte and ends on the last byte. Second byte being 99, first byte being 4E. Let's let this run. It's probably going to take another second. Okay, cool. And we can see that it ran. Okay, cool. So this got ported over to Python 3 and it works. Just going to copy this over here. That was a little bit of a pain to do. And when we run the exploit, let's copy that. Oh, wait, no, we did that wrong. And let's copy this portion up here. Okay, cool. So other than the wrap gadget stuff, which I'm going to do right now, we've ported this. This episode is over 40 minutes long, so I'm going to cut it off here. Thank you, gamers, for watching, and see you later.